Okay, last class we were discussing DFT. In fact, we discussed block LMS algorithm, and now I told you that I would go into a first implementation of block LMS algorithm using FFT, and then I started with the definition, theory of DFT, how DFT comes, and then I said that if there are say two finite length sequences x n and h n, one of length capital N, another of length m, capital M, n and m may not be same, then x k, if we take say in fact, I said that if there is x n and there is h n and there is y n, and suppose x n and h n they are of different length, but I add zeros to make them equal length. Okay. Whoever is shorter, I add zeros to that, some extra zeros, so that both of them are same length and length is equal to capital N. So, I take n point DFT multiply the 2 DFT, that will be again a sample of the DTFT of this, but if I take the inverse DFT, I DFT of those samples, I do not get y n, because y n is a longer sequence, its range is not capital N, 2 n minus 1 is the length, 0 to 2 n minus 2. Then question was, even if I do not care further, I still persist with this, that okay, I will do x k into h k and take IDFT. What do I get for y n? I get an n point sequence, but what is it? Is it how much of it is coming out to be linear convolution, and how much is the error and all that. So, we worked it out. Okay. We found out that if you do x k, h k and call it say y prime k and take n point say y prime n as n point I DFT of y prime k. This y prime n expression we found out. Remember, there was a linear convolution component and there was another component. Y prime n was, one was this, say maybe you can write in this way. What was, which way I wrote, x n h 0 or x 0 h n? X n h 0. This was the linear convolution part, and then there was another term as h crosses go beyond n plus 1, you have got x n minus 1, summation should be small n plus capital N, then h n plus 2 x n minus 2 plus dot 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 plus h n minus 1 x what n plus 1, isn't it? X is coming down from capital N minus 1 to capital N minus 2 dot dot up to small n plus 1. This is going up further, right. This first part is the linear convolution component you have seen, but second part is the error. That is why together it is not linear convolution, together it is called periodic convolution or circular convolution between x n and h n. Now, I will show you a graphical way. I think that is where I stopped last time, a graphical way of evaluating it. Okay. I will just dictate the steps. Out of the two sequences x n and h n, both are of length same length. You hold one of them as it is and make a periodic version of the other one. So, that means whatever you have in one period of length capital N, go on repeating it in left and right, to the left side and right side, it becomes an infinitely long sequence. After that, the next two steps are common in linear convolution. You reverse it, reverse the entire infinite sequence. Mind you, after reversal also it remains periodic. A periodic sequence, when you reverse it, time reverse it, it still remains periodic. And then you shift this by that amount at which you want to carry out the convolution. Like here you are finding out the convolution at n. N can be 0, 1 up to capital N minus 1, that is our range. So, shift it to the right by small n. After that again you still have an infinite length sequence. Now, you throw away the components outside the window from 0 to capital N minus 1, to the right and to of capital N minus 1 and to the left of 0, whatever you have, throw it away. So, it again becomes a finite length sequence. So, two finite length sequence you have h n as it is and one obtained from x n in this manner, and now go on multiplying samples from top and bottom, add them, you will get the circular convolution. That is my claim, and we will have it verified that that will indeed give you this expression. Okay. So, let us do that, and mind you I will not go through all the steps, I rely on your intelligence, so that you can visualize how I am getting a sequence like this and all that. Okay. Otherwise, it will become too lengthy and clumsy also if you have to draw too many diagrams. So, H I write as it is, say maybe H rod, where n I reserve for computing the convolution, n is an index at which you want to find out the convolution. So, n is your choice, which means fixed, n cannot be variable. So, call it H r then. Okay. Plot H sequence as a function of r, not as a function of n, because n is your choice here, you have to find the convolution at a specific choice of value of n. So, n is fixed, that is why I am writing it A r. Okay. Then what I will do, whatever I have for x n, x r rather, x r, I will make it periodic, fine, and then I will shift, reverse it, and then shift it by an amount, and then chop off portion to the right of this, to the left of this, and sample wise multiplication addition. So, for the time being I will start with 0 shift, then 1 shift, 2 shift. So, 0 shift only. If it is 0 shift, what I get here is x 0, then to the right I had x 1, x 2, x 3 like that, because of reversal it will go this way, x 1 dot dot. What will be here? At n minus 1 again this x 1 will come, is not it, x 0, this is x 0 at 0th point, again at nth point there will be x 0, is not it. So, here x 1 dot 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 up to x capital N minus 1, like x 0, x 1 dot 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 x capital N minus 1, is not it. So, this is x, I am sorry it is becoming clumsy, that is the problem with this n minus 1. Can you see this is n minus 1? I am sorry it cannot be bigger here, 0 shift, and now I throw away to the any component to the right of this, to the left of this, to the right of capital N minus 1, to the left of this, just multiply. Obviously, you have one term x naught into x naught into h 0, x naught into h 0, this term. Okay. Plus you have, you see, x capital N minus 1 h 1, x capital N minus 1 h 1, and so on and so forth, h 2 x capital N minus 2 dot dot dot. Okay. Are you with me? Isn't it? Small n is 0 here. So, 0 plus 1, 0 plus 1, you are getting it. Now, if I shift it by 1 and then again chop off quantity to the right of this point and to the left of this point, this was for n equal to 0. Okay. For n equal to 1, we do once or twice, it will be very clear. For n equal to 1, this x 0 will come below h 1. See that part is like linear convolution, x 0 comes below h 1, x 1 comes below h 0, and sample wise multiplication, is not it? You have shifted, so you understand x 0 has come here, x 0 into h 1, x 1 into h 0, that part is like linear convolution. So far so good, this is okay. And then n minus 1, x n minus 1 will go below h 2, and this x 1 will move out. Are you following me? X 1 will move out. So, you have got again this form. In general, now you can see, in general, if you shift it to the right by n bit, x 0 will come below h n, and therefore, below h 0 will be x n, distance is same. So, that part will be obviously x n h 0, x n will be here, is not it? H 1, that means before x n there is x. Are you getting me? This is very simple. H 1 dot dot dot, this x 0 has gone over to the nth point, this is n, this is where x 0 is now. So, x 0 into h n. Okay. I have shifted, and then to the right of this is x capital N minus 1, x 0 is here, to the right of this is this fellow, to the right of x 0 is always x n minus 1. So, this fellow, then x n minus 2, x n minus 1 will multiply what? H n plus 1th, if it is n, this is n plus 1th. So, h, and in this order, is not it? In this order, h n plus 1, h n plus 2 up to this, and recurrently this will go up, this will go down, this will go up, this will go down, summation remains. So, dot dot dot, you get this. Okay. If you have question, you can ask me. I did not show so many diagrams and all, I thought by now it should be clear. Okay. So, this is a graphical way of doing convolution, but you understand there is a problem. This error thing comes, though it is not part of this adaptive filter, but just for educating you people, let me tell you how to get rid of this quantity. So, this is not something we need here. So, that is why I draw it on the back side. That is, by using this DFT technique only, I want to find out the linear convolution. Then what do we do? Suppose x n is of length capital N, this is of length capital M, and n is greater than m. What I will do? I will be adding some zeros to both, because what is the length of y n? If it is length capital N, if it is length capital M, y n length is n plus m minus 1. So, I am to make these and y n same length. That means, this was length capital N. So, I add m minus 1 zeros here, capital M minus 1. This was length capital M. So, I add capital N minus 1 zeros here. Now, if I convolve them, I still get same sequence, but zeros do not change any result. Okay. So, all are of the same range, but then the question is, does it, if I carry out then now, I mean the IDF DFT means how many point DFT? N plus m minus 1 current length, you call it capital L. So, L point DFT, L point DFT, L point DFT multiply L point inverse DFT. If I do, I get a L point sequence. Is it the linear convolution? Is it that if I carry out the graphical method, I will have this disappearing then? That is the thing. We have to verify. If this disappears, wonderful. Then that will indeed give us this part only, linear convolution. Okay. So, this we need to verify. So, what we did, your h n, h r rather, it was up to m minus 1, and then I have 0, 0, 0, 0, 0, 0. How many zeros? Length m and n minus 1 0, because m plus n minus 1 is the length of linear convolution between x n and h n. That is, output y n has a length of this, you can call it capital L. So, I want to make both the input signals to be, both h n and x n to be of the same length. So, I appended extra zeros. Already it was m, now n minus 1. So, m plus n minus 1, its length is L. Similarly, I do the same thing for x. X plus n minus 1 how many zeros? M minus 1 zeros. I have to now do circular convolution between the two. Okay. Very simple. I will follow the graphical method. I will hold this top one as it is, make a periodic version of this, reverse, shift, and then chop off the right side and left side, right of this point and left of this point. This point you can call L minus 1, 0 to L minus 1, length is L, and then sample wise multiplication addition. Okay. So, if you do that for 0 shift, say for n equal to 0, what will happen? This x 0 will remain here. Please say this figure is very important figure. This x 0 will remain here. This entire thing will be folded to that side. So, that means these samples will go, and to the in the front will be this 0 pad. If you fold this that way, this part will be folded back, right, x 0 x 1. So, here will be x 1, here will be x 1, dot 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 up to some point, then 0 0 0 0 0. Same thing will repeat here, periodicity. So, this 0 pad m minus 1 will be here, m minus 1 means the 0 pad will coincide with this point, length is m. So, it will coincide with that point, and then there will be some data. This will be x 1 to the left of x 0 here x 1. So, again from using periodicity this is coming on this side, x 2 dot dot dot, this is x n minus 1, and now chop off right and left, multiply. These zeros will take up these fellows, and these zeros will take up these fellows. So, only you get x 0 h 0. So, n equal to 0. This is called 0 padding technique, 0 padding. That means n equal to 0 means only h 0, which is a linear convolution, correct linear convolution result, isn't it? You understand these zeros, how many m? M minus 1, m minus 1. How many samples here? 1 is already here, so n minus 1. How many zeros? N minus 1. Now, we shift it to the right by 1. The 0 will shift here. One data will be out, rest of the data will be again multiplied by 0. Only these two samples will be taken care of by the which one? X 0 will be fall below h 1 now, and x 1 will come below h 0, linear convolution. All correct result, and I go on doing it. After, as I go on shifting, some data again some data will go out, this 0 keeps moving. Okay, 0 keeps moving, 0 comes to this side, and data comes, as long as this data comes here, no problem. They will multiply, like x 0 will move further to the right below h 2, x 1 below h 1, x 2 below h 0, you get convolution result at 2. Subsequently, this 0 part of the samples will be multiplied by zeros, part of the samples will be this sample will multiply by part of these zeros, so on and so forth. After a while, what will happen? This data dot dot dot, after a while, as I go on shifting, you will have a situation where this data has come here, but to the right of this. I mean, this is the data block. Dot dot dot. So, that means here also, and I have got some zeros here. This entire data in one block means remaining points have to be 0, some zeros and remaining zeros here. These zeros will make sure that nothing comes from top, and these zeros will take care, these zeros are colliding with these zeros, no problem. So, essentially you have x 0 coming with the, I mean you will get linear convolution, isn't it, normal as you do in linear convolution. Finally, this will come over here to the right at this point, x 0 finally will come here, and that time x n minus 1 will be last sample, last here, to the left will be zeros, and that will be last result of the convolution. Do you understand? It will give you perfect linear convolution result. This is called zero padding technique. In your DSP, you should have studied this. I am sure you have not been taught, isn't it? Circular convolution by Anyway, another result. Now I come back to my context. Another result, we will just present the result and store that result somewhere for our future consumption. Okay. Suppose I do not do zero padding in both, whichever is the shorter one, I add those extra zeros only to that guy, so that both the lengths are same, and then do circular convolution. Obviously, I will not get correct linear convolution result, but it is still something better than not doing any zero padding at all, isn't it? So, what will I get? That is the question. Suppose I have got a situation like this. Say H r say X r, input I always take to be bigger, and this H fellow up to this length m, length n, length m. What ideally I should do? I will add m minus 1 zeros here and n minus 1 zeros here, then make a bigger sequence, convolve. I mean, if I do the circular convolution, I will get the correct linear convolution result, fine. But suppose I do not do that, I say okay, the bigger guy I will not touch, let it be as it is. I will add some zeros only here. How many zeros? Length n, length m, so obviously n minus m zeros, and I say that I will do a circular convolution between the two, means I will take n point DFT, n point DFT multiply n point I DFT. What will I get? That is what I will get graphically by that circular convolution. I want to examine what it is. Whatever I get, that is n point sequence. Is it that part of that at least is correct, or no part, no point I get correct linear convolution? Everywhere I have got the error component. But we will see that part of that output gives you correct data, correct linear convolution result. We will see that, and some portions you will get wrong result, and we will identify where correct, where wrong. Okay. So, suppose I do the circular business. So, I will be making periodic version of it, reverse it, and then 0 shift, first shift, and always chop off portions to the right of n minus 1 and to the left of 0, sample wise multiplication for top and bottom, and add. That is a simple follow. So, if I do that, H 0 and then zeros, this is 0 pad here, is not it? That means, here is a 0 pad, 0 pad of how long? N minus m. This sample n minus n, and then I have got other samples. Which one? If it is h n minus 1, h what? H m minus 1. So, this is m minus 1. So, here also I have got h 1. This is my area of interest. Now, you can easily see I will not get correct result. Why? Because correct result means for the 0 shift, I should have only h 0 into x 0. These samples are taken care of, some samples coming from here, these zeros, but these guys are not taken care of by some 0 here, because I did not place those zeros. So, I am getting incorrect result. So, at n equal to 0, incorrect, n equal to 1, I am not bothered about the correct expression, I just want to find out where correct, where not correct. Correct means against linear convolution. So, at n equal to 0, I am get erroneous result as far as linear convolution is concerned. Okay. At n equal to 1, okay, these two will move up, this 0, one sample will be moved out, but still these fellows are there, they will multiply with the samples from top and then will give rise to error. This left of 0 pad is fine, h 0 below x 1, h 1 below x 0, that is the linear convolution thing, is not it? But these fellows are creating trouble. So, this will be incorrect, dot dot dot, it will continue as long as, I mean, till the point where this 0 pad reaches here. from that moment, at that moment I have what? H 0, H 1 dot dot dot, how many? How many shift? M shifts, M shifts, because H 0 I had this much, okay. H 1 M shift of obviously, total n minus m zeros here. This point is my n minus 1th point. So, this way I can find out what is this point m shifts. After m shifts, I will have a situation like this. What will be this point? H m minus 1, no? H m minus 1. This folded portion, this will come out. 0 shift you are here, 1 shift you are here, 2 shifts after m shift, this will be here. If at 0th point m minus 1, this is m minus 1th point. Okay. Length is m, all the m data have to fit in. So, you have got fit in, and that is why only then you have got the extra, this entire 0 covering up the remaining place, isn't it? This entire thing, number of data, how many? M that have come here, and that is why n minus m, this 0 block perfectly covers the remaining part of this. That is the time when no such data will create trouble, because they are multiplying zeros. Okay. Earlier, to the right of the 0 pad I had a sample, like to the right of 0 pad I had some samples, they are multiplying with samples from here, they are creating trouble. But now, this is finally pushed to this length n minus m, total is n. So, how many samples here? M means the entire block has come here. So, H 0 H m minus 1. So, at 0th location m minus 1 is sample. So, at m minus 1th location 0 is sample, is not it? So, this will be what? This will give you the output from n equal to m minus onwards, correct output. After this, you shift it to the right, but who will enter from here? Again the 0 pad, is not it? Finally, dot dot dot, a time will come when again H 0 will come here, H m minus 1 will come here, and this 0 pad will fully fill up this place. Lengthwise, you see, total length has to be n, this is m, this is n minus m, and again this will take care of these fellows. So, from this point onwards till end, till the last point is n equal to n minus 1, I have got correct result. So, how many? For n equal to n minus 2, that means first, this is incorrect, first m minus 1 points are incorrect. Okay. So, again let us sum up. There are two sequences, one shorter, one bigger. Shorter one I added extra zeros to make its length equal to the bigger ones, and then I followed a circular convolution. In that circular convolution, I still get a length and sequence, out of which first m minus 1 points will give you wrong data, first m minus points. After that, that is from 0th to m minus 2th. From m minus 1th, you will start getting correct linear convolution result till n equal to capital N minus 1. Remember this result you store somewhere. Okay. I will be making use of it later. Now, let us do something else from very basics of DSP. There is a technique called overlap and save. Overlap and save method. Suppose you have got a very long, forget about all this, even DFT forget about for the time being. Suppose you have got a very long input sequence, but there is an FIR filter. You have to find out the output. So, at each point you have to go on doing convolution. So, at so many points you have to do convolution, so much of computation you have to do and to find out the total output. So, whole task can be made much simpler and faster computationally by some technique. One of them is called overlap and save method. Firstly, before I go into that, certain basic things of DSP you see whether you can foresee. Suppose there are two sequences, one is here, another is here. You call it say x r or x n, does not matter, you call this h n. You get a convolution. See, I have drawn it like this, that is causal. It is not necessary that they have to start at origin, they can go beyond to the left also. My result does not depend on this shape, just a sequence, two sequences. If you convolve, you get something. We know where it will be located and all those things we know. My point is, if x n is, suppose instead of this, if this is this x n is shifted here, that is this goes to a point say capital K, not K, K have used for DFT, say again n, this entire thing n, this guy is come here and I am convolving the two. My convolution will be, result will be same because data has not changed, but the location at which the output will be placed will be what? Shift by the same amount. Earlier, if the output were positioned here, it will not be shifted by the same amount. If you cannot see this graphically, you can just suppose go into the z domain or z domain say. Convolution in time domain means multiplication in z domain. Z transform of this into Z transform of this is the Z transform of the output there, fine. What I am doing here, I am delaying it by capital N. So, same Z transform multiplied by Z to the power minus n into Z transform here. Now, Z to the power minus n you keep aside, again then Z transform of this into Z transform of this, which is the same output, and that multiplied by Z to the power minus n means this output will be shifted by capital N. See, Z domain is very easy to work out. Okay. So, I can conversely, if I am convolving two guys which are separated like this, then I can make life simpler by simply shifting it, aligning this with origin. Okay. Convolve, calculate the output and again shift it back to by capital N. So, again next time I can convolve with some other person here. I will again shift it back to origin, convolve, get the result and again place the output there. This way I can do. Isn't it? Another important thing, suppose, and this is what books do not mention these aspects. This is very surface, Oppenheim and all, they missed out this point. Suppose this is data, this data I am segmenting like this, and there is one sequence I am convolving with. Fine, you know how to do linear convolution, you will be reversing it and then multiply sample wise, shift it again, multiply sample wise, shift it, go on doing it. You will get an output from here to some point to the right of this. We all know convolution. Suppose this data I break like two components. One component x 1 n, this was x n, another is, and this is h n. This length is 0 to m minus 1. This is x 2 n. I am saying that first I will convolve between these two, find out the output. Take the output from here to here. The output will be the convolution, output will be what? Output will be going to the right. And again I will convolve between h n and this. I will start here, I will go to the right. Then here if I take data from here to here only, output from here to here only, next output I take from here. You understand? If I convolve between h and x, result will be something like this up to this point. If I convolve between h and x 2, result will be like this. If I say that I will take the output from here to here, then I will go here and take the output up till end. Will it be correct? Answer is wrong, because when I convolve between h and this, I am reversing it. Okay. But to the back of this, to the left of this, there is no data, whereas in effect when I was doing convolution, there was data coming from this side, that was getting multiplied by part of this, that will be missing. is not it? That means, here if I do this convolution at this point will be wrong. Still again at this, if I suppose reverse it, if I reverse it 0 to minus of m minus 1, that entire thing comes here. Okay. They multiply by 0 here and only one sample. So, you get some result, but that is wrong, because in effect there was no 0, there was data, but you have made it 0 here. Fine, you understood there is wrong, there is something that is wrong. You go for the next one. Still partly it will be 0 here and only 2 valid data are coming, is not it? So, still that output will be wrong. When will the output be correct? When after getting shifted this entire thing has come below this, then you do not need any data from the previous block, is not it? When will that be? After how many shifts? From mth shift onward. So, that means, if the origin were here for the 0th sample, first sample, second sample, third sample, if I align everything to origin say, then here 0th, first, second, third, fourth up to m minus 1th will be wrong, mth will be correct. Remember, there was also a different context, figure was same, m minus 1 up to m minus 1 was wrong, mth was correct. Two different contexts, but just figures are, look at the figures. Okay. Now, I propose a technique to carry out this long convolution, that suppose I break this data like this, I will have an overlap. This is my 0th block, next block, in the case of block adaptive filter, this will be that block, by the way. Next block, instead of starting here, I come back, how many points inside? M minus 1 points inside, and go like this. That is, here I have overlap. Data is same, I am just showing as a two kind of strips. This is one strip of data, and the last m minus 1 components again repeated in the front of this next block. There is block number 1, again this guy is repeated m minus 1 length, second block dot 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 dot. Now, if I do that, and now suppose I am convolving with a small filter H n whose length is capital M. Okay. Here again, to make life simple, suppose we really started here, to the left is 0. So, to the left there is no problem, you can reverse it, this is your H n, this is your H n. So, you can reverse it, indeed here I have 0. So, there is no problem, you go on doing convolution, you get result. Here also at this point, at this point, at this point, you go on doing the convolution, you get correct result, because all the previous data needed for this convolution is already available in the block. Fine. So, you get one set of output, place it here, output, you placed it. Now, you are convolving, now you take this block, with this block you want to convolve. Firstly, you can first shift the block alignment, align with the 0 thing, then convolve, whatever result comes, that you place back here. Okay, just for making life simple. So, suppose I am now this is indeed the 0th, I mean this is the vertical axis, this is the origin, you are convolving between the two. That time again at this point, at this point, at this point you get result, but will that be correct result? Answer is no, because to the left of this I have now 0, but originally there was data. So, that those output I ignore. Who will supply me the output? From the previous block computation I already computed them, I stored them, saved them, that is the overlap and save, saved them. So, at these points I get incorrect result, but I ignored. Only from this point onwards I get correct result, I stored them till here. Okay. So, this will be my in the adaptive filter block adaptive, this was 0th block, one filter weight, slightly different from this context, because I am keeping the filter to be same here, convolving always with this guy, whether this block or this block or this block. In the case of adaptive filter, when I convolve with filter have got one filter weight, when I go to the next block weights values have changed, but weight values really are no concern to me, is not it. So, their blocks will be overlapping like this. At these points I need output, but that output will correspond to the filter weight for this block, and that I already obtained. Are you following me? Filter weight for this block I already had obtained. For the, I mean, I will take the output at these points corresponding to which filter weight, the weight assigned for or for 0th block, that I have already computed in this convolution. I saved them. Now weights have changed. I start again at these points. Firstly, these points give me wrong result, even if weights did not change. Now weights also have changed. So at these points, the output really I do not want. Are you getting me? But I will not need them, because they are already computed. Correct desired things already computed. I will throw them away. But from this point onwards, I need the output for this block only, with the filter weight obtained for this block, and that I am doing, because for that I do not need any data from to the left of this. So, that is available and I happily do it. So, that means whatever is here, that I will discard, whatever is here at the output I will discard. That is output, if you place like this portion you discard, again output if you place like this portion you discard. Now, I want to do it by FFT. What will I do? One thing is, you can tell me, sir, you want to do after all you are doing filtering between this, I mean convolution between this block and this entire block, is not it? This is of length say n, this entire length is say n, this entire length is m. So, you can tell me, sir, we all know zero padding technique. As long as you are convolving between this and this, you will finally throw away the first few samples, I agree. But before that, let us carry out the convolution between the two. Only the first m minus samples are wrong, we know, because they are assuming 0 values to the left, is not it? Whereas, actually there are data and they are assuming same filter weight, or so filter weight has changed, I am putting back the correct. But even then, first we calculate the linear convolution, then only I will throw away this part, is not it? So, you can tell me, look, fine, you want to do a linear convolution with this block of length capital N and a block of length m, fine. You add zeros to this guy also in your calculation, m minus 1 zeros, you add zeros to these guys also, n minus 1 zeros. So, n plus m minus 1 is the length, fine, that will work. DFT, DFT, IDFT, you get the full output, and there you throw away these samples. I agree, but instead of n plus m minus 1, this many point of DFT will have more computation, is not it, than nth point DFT. Nth point DFT much less computation, n plus m minus 1. I say that I can use simply nth point DFT, because what I will do, I suppose this block you are taking, this block you are convolving with this guy. What I will do, this is a shorter sequence, this is a bigger sequence, longer sequence, I will add only zeros to this fellow, n minus 1 zeros, and do circular convolution between the two blocks. I just showed you previously that even there you get incorrect result only in the first m minus 1 points only. From mth point you get the real linear convolution result between this block and this block, and that is what I want, because from this point onwards convolution between this and this is enough. I do not need any data from here, is not it? So, two things are matching. There are also m minus 1 points you have to ignore, and I am already ignoring. Afterwards, you get the real convolution, linear convolution output between this and this, and I am interested in that linear convolution, because at this point, at this point, at this point, when I convolve, even when the data is contiguous and all, there is no contribution from this tail. This much is enough. Are you following me? When you suppose this is the origin, you first reverse it, all zeros are coming, because on this side zeros, incorrect result, but as you moved it here, from this point onwards, You need purely linear, the linear convolution between this and this is enough. I do not need any data from here, that okay, you can say that look, originally there was some data and now you have got zeros only. So, you are getting incorrect result, that does not apply here. Okay. So, simply linear convolution with the two block can be acceptable in the final result. Second, that figure m minus 1, so m minus 1 I do not care either way. This is called overlap and safe technique. You see, I just live happily with n point DFT only, not so much n plus m minus 1. You see, these are the DSP tricks. And I mean, I wish I could read some papers. Some papers have come up recently where it can be still manipulated to be less than this. Some papers are there. I only did not study under the assumption that data is real and all that. It can further reduced. I mean, some further optimizations are possible. Let me see if I can find time to read some recent papers. They have come out. Okay, this is overlap and safe. So, you understand how it will be used in the adaptive filter case, not weight updating I am talking of now, I am only talking about the filtering part. For this block, one set of filter weights, for this block another set of filter weights, but for this block say this is the filter weight. I have to convolve between this and this block. At that time, at this point, from this point onwards, to get the output, I do not need data, any data from this block, because this previous m minus 1 as available here is enough for me. Then what will happen for the computing output here? Firstly, if I have to compute the output at these points, I will target this block. These points come under this block, therefore, the filter weight for this block, but that I have already calculated in the previous round, that I have saved. Are you getting my point? So, this is how you can simplify this computation in the forward path, filtering path, but the more challenging thing is the weight update part. Weight update part I will have to continue till tomorrow. I can just briefly show certain things.
Sir, in the 0th block you have to do full length.
Yeah, right. Right. 0th is starting block, let us say, yes. Yeah, in starting block there is no question of throwing away something, because there is nobody to replace that with, isn't it? Okay. In the block LMS algorithm, there are two things. One is filter weights are fixed for the block, and you are doing filtering, means there is a block of data, it passes through the FIR filter. That is what we did now. You have to do linear convolution, and you can use FFT by choosing the blocks in that overlapping manner. There is one block, another block, there is an overlap of m minus 1 samples, if the filter length is m minus 1 samples, and that way. Okay. That much is clear. Now, weight update part. In the weight update part, you can see one thing. Let me write down elaborately W n plus 1, not n, W I plus 1, because it is block LMS. There is no question of updating with time n, updating with block index I, plus was it mu by L, what notation use, mu by L or mu prime by L or something, call it mu, because that is of no use here, just any constant will be, is a computation I am bothered about. It was I, no, not I, which notation used here, J, is it, because I is used for the block index, R equal to 0 to capital L minus 1, capital L was the length of the data block and capital N was the length of the filtered. L was suppose you have taken to be longer than n, though I do not see it to be necessary. Okay. And we have got these things, x vector by the way, if it were a complex LMS algorithm, then we can see one thing, whole derivation would be same, but there will be a star here, isn't it, x star, or star on x or star on e, star on e. We will be considering that extension, because when I do this FFTV business, I have to finally, I will take care of that also when it is complex. For the time being, we are assuming real. Just look at the data structure here, what kind of thing is happening. These are all data vectors. E, so this is one vector I write, this is the starting point of the block, but before this how many points? So, this is that overlap zone. I will take the last n minus, not m anymore, filter length is not m here, it is n, capital N, I have just changed it. So, last n minus 1 data from the previous block, they correspond to that. In my modified scheme, they have got appended with current data block. Current data block earlier was starting here, but I have appended this part. Only thing output at these indices will be ignored, okay, because of the thing which I have been discussing so long. This is my x, this data vector for r equal to 0. This will be multiplied by, this is multiplied by E I L. Okay. Next block is, you understand, I L will go on, I L plus 1, okay, dot dot dot, dot dot dot. See one thing, consider the first row, because after all, after multiplying you will be adding them. You will multiply this entire column by this, entire column by this, and so on and add, you will get a column vector. So, consider the first row or first element of the column. How will you get that? Just the first entries, this fellow into this fellow, this fellow into this fellow, dot dot dot, this fellow into this fellow. Okay. Next entry will be what? This sequence remains same, but this sequence gets shifted to the right by 1, you see. I L has moved here, I L plus 1 here, and I L minus 1 here. Isn't it? And multiplication, it is like this, isn't it, that suppose I have some zeros, how many? N minus 1, n minus 1 zeros, and then I have got E I L, I put E I L plus 1 dot dot dot, all these terms, E I L plus L minus 1. Suppose I do that, and this entire data starting from here, I go up, I put this at the origin, then go up this manner, put them here, I L minus n minus 1, then dot 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 up, I L, then I L plus 1, I L plus 2, I L plus dot dot, put them here. No books will explain like this, please be with me. I have put some zeros.
No, okay, sir. In first block that was I of IL minus n minus 1.
Okay. N is the length of the filter, not m anymore. In adaptive filter, it is n, not m. Okay. And what I am doing now, I am taking this data from here, 0th data, first data, second data, dot 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 dot, like this. So, n minus 1 and then L. So, this data will be here. Here dot dot dot, this is okay, and then your normal these fellows x I L, this guy. Suppose I multiply the two sample wise and add. First, what will I get? What I was getting here? This into this, because after all E I L only will multiply x I L, other fellows are 0. This will multiply the next guy. So, these fellows will not come into operation. I will get the first entry, this into this plus this into this plus dot dot this into this, first entry. For second entry, what we will have to do? If I shift the entire thing to the right by 1 bit and send in a 0. Suppose as though there are zeros here, send in a 0, and then within this zone I multiply top to bottom and add. Will I not get? So, it is like that intermediate step of graphical way of circular convolution when you have reversed it and then shifting and chopping off. So, if this is the reverse version, what is the original version? You understand? I have to use the circular convolution. Are you following my this thing? Anyway, time is up, so I will just throw away this question. This is what we do in that intermediate stage of circular convolution. First, no shift, multiply, then shift by 1 bit, but chop confined within this only. From here, if I can send in a 0, that 0 comes in, one data goes out, this data goes out, this fellow comes here, this goes out, previous fellow comes here, and again you multiply, add, and go on doing it, isn't it? That is what we do in the circular convolution at the later stage, in the computation stage. So, that means, this is obtained by reversing something. So, what is that something? That I have to look at. Okay? So, I stop here today. So, tomorrow I will begin here. Okay, thank you very much.